So welcome everyone. Today we have Maja Resman from Zagreb, and she'll talk about classification of Dulac germs. Thank you, Maja.
Thank you. I come from the University of Zagreb, for those who don't know me. And first, I would like to thank the organizers for inviting me here. I'm really glad to be here and to give a seminar. I will talk about, I will provide the title. I'll talk about the part of ongoing work. This part I did with my collaborators, Pavel Mardešić from University of Burgundy, Jean-Philippe Roland from University of Burgundy, and Vesna Županović from University of Zagreb. I will first tell a little, so I deal with discrete dynamical systems. So I will first give a little bit of motivation. What we consider are hyperbolic polycycles. All singular points are of the saddle type. And standardly, first return map is considered around this polycycle. So on some transversal, we look at the trajectories that are very close to the polycycle, and we suppose that we don't have, that we have sort of monodromy around, so that there are spiraling trajectories that come back to the transversal. And then we can define what is standardly called the first return map. I hope you're all familiar with. If not, I explain a little. So we put coordinate S to the transversal, and this is 0. And suppose that the trajectory is attracting. What we consider is a mapping F of S that goes from S to the next point where the orbit, the trajectory hits the transversal. So this is standardly called the Poincare map. So this is related to the famous Dulac and Hilbert's 16th problem. I will explain in a few words what they are about. But first, this Poincare map, as we consider it, is formed as composition of finitely many maps. So the first one is map around the saddle, then a regular transition map, then again a map around the saddle, a regular transition map, etc. So F of S is a composition of, let's say, regular and what we call a Dulac corner map. So, for example, R and at the end. So this Dulac map is considered as a saddle. We all know that locally, a field around the saddle can be written as, we are in real dimension, 2, like minus alpha y, where alpha is bigger than 0. So this is a linearized saddle, but usually it has an additional terms. So what can be seen when we solve the equation to get, I will not solve it now, but to get the map going from here to here, we can easily see from the first equation that the time that we need to go from this transversal to this transversal is logarithmic. So just solve this first equation. So what happens is that in the case that, so now if alpha is irrational, we can linearize the field. If alpha is rational, we cannot do it. And then by a little bit of work, we can see that in the irrational case, we will get a Dulac corner map without logarithms that has real powers of x inside, but or s inside. But in the case where, for example, alpha is equal to 1, alpha is rational, we get logarithmic terms in it due to this logarithmic time that appears. And then a final form given by Yashenko, Dulac etc. Standard form on this first return map around the hyperbolic polycycle can be written as this. So this is some alpha 0. This first term does not contain logarithms, and these are polynomials. So this is just asymptotic as x goes to 0. It's not a convergent series, and it is defined on some small neighborhood of 0. This is polynomial in minus log x. So it's not a trans series really. It's actually expansion series. Okay, so these alphas are strictly increasing and tending to plus infinity. So there is a question. There are two problems that are suddenly considered. One is the Dulac problem, and the other is Hilbert's problem. Here I will not go into much detail. Dulac's problem asks if there can be an accumulation of limit cycles. Limit cycles are closed periodic orbits that are accumulated at least on one side by spiraling trajectories. If there can be accumulation of such orbits to the polycycle. So it's a static problem. And then Hilbert's problem asks about bifurcations. So once that we bifurcate the vector field around this polycycle, so even connections can break, can there appear infinitely many limit cycles, and if their number is bounded somehow by the degree of the vector field that we consider. So I will not go into much details here. I will tell a little bit about Dulac's problem. So what we see that limit cycles that I talk about are recognized as fixed points of such a first return map. So actually the question is about the multiplicity of fixed points of this germ at 0, or the multiplicity of 0 point of the displacement map f of x minus x at 0. So the first what we can tell is the following. We suppose the case, also the other case is treated, but we suppose the case where f of x is not identity, does not expand as an identity, because this is more difficult to treat. So we suppose that we have something after that. And what we can see from this expansion is somehow, if this expansion determines the germ explicitly, so if we can have injectivity, so that different asymptotic expansions in this power logarithmic scale cannot give, so two different germs cannot expand in the same power logarithmic scale. So this is the injectivity that we would want. So if we have this, we see that if germ has behavior like this, it cannot have accumulation of limit cycles, because otherwise it should be yes, it should be.
So the F here is the Poincaré map. It's not the Dulac map. It's the whole.
It's a Poincaré map.
Okay.
So what we call Dulac map, actually, I will come to it. So the germs that expand in this scale and have expansion property to sufficiently big complex domain, we call Dulac maps. They are usually called almost regular, or almost regular, or quasi-regular, or something like that in the Yashin code. Okay, so the problem is that somehow once that we know that f is uniquely determined, so that f cannot, if the expansion is identity, or if expansion is 0, then f is equal to the identity or equal to 0. If we know that, we can conclude, on basis of the first term, that we cannot have accumulation of limit cycles. But the problem appears if we cannot conclude that. Basically, if we don't know any other property, this germ is defined on a real line, we cannot conclude it, of course, because we can have you're more familiar than me because you do such things. So if we add any exponentially small term at 0, we have the same expansion in the power logarithmic scale. So evidently, having expansion of the real line is not sufficient. So what we have to do is basically just to give you some sort of intuition. If we prolong, let's say this germ is defined just here. Suppose that we can say that we have an analytic germ in the complex plane that expands like this. Once that we somehow make sufficiently big sector, this part is not anymore small. So actually, this is sort of idea to go to the complex domain to find sufficiently big domain that so that we can say that germ is uniquely determined by the asymptotic expansion. So this is the idea of Ilyashenko's standard quadratic domain. So using this equation of a saddle and passing to C2 to complex field, somehow he managed to show that the germ, the first return map can be extended analytically to a standard quadratic domain. So now I will define what I call Dulac germs and what is in Ilyashenko's work called almost regular germs. So these are germs. Now I will pass because of convenience. So let's see the problem. So this F is defined at the real line. And now I want to go to the complex domain. And I will consider the germ not in this chart, but in the logarithmic chart. What I mean by logarithmic chart is psi is minus log x. So passing to this chart, what I do is a change of variables. So I have to do, let's say, size minus log x, I change variables on both sides. And when I do that, and write this in a variable psi, we get a alpha 0 psi plus something exponential or logarithmic in a, some constant in not anymore a, but some transformation of it, plus sum of these become exponentials. And for the same pi I, a little bit transformed, like also a polynomial, let's say y. And now these are also beta i's that are somehow formed as integer combinations of ratios of hyperbolicity of the saddle. So they are finitely generated as integer combinations of ratios of hyperbolicity of the saddle. All of them are bigger than 1 and tend to plus infinity. So this is also asymptotic. Now, as psi goes to infinity, or since we are on some specific domain, we can say that it's equivalent to this condition. What we ask of these germs is that they admit asymptotic expansion of this form. For example, for psi, now psi is minus log x, so this interval, small interval around 0 in x, is sent to some neighborhood of infinity on the real line. Let's say as psi tends to infinity. Also, they can be extended standard quadratic domain. Standard quadratic domain is an asymptotically defined domain which looks like this. So I can write the exact formula, but it will not help much. So we saw it, I think, yesterday. The exact formula: one takes c plus minus some disk of radius, let's say r. So parts of C plus that are of modulus sufficiently big, and transforms it by a function like this, and then we get a domain like this. But basically, most important thing is that this sort of it behaves like a law asymptotically. So such domains, when we go back to variable x, now what happens? Since this is a logarithmic chart, we go back to z to x variable now becomes z complex variable, and each so let's say this is part in between minus pi and pi, then another 2 pi, then another 2 pi. We can represent it on the Riemann surface of the logarithm back in the z variable, so that we have first, let's say here, we go here and then to the next sheet and next sheet, but the radii becomes smaller and smaller, and also on the other side like this. Okay, so we can, so the problem with the Riemann surface of the logarithm that we cannot sum up the things, and somehow this chart is much better to work with, and it is a universal color, so everything can be done here. And also there is another condition that this germ, let's say this is now f of psi minus alpha 0 psi is bounded on this domain. Okay, so under these conditions, Ilyashenko proved that we have what we call quasi-analyticity property. That means that once that we know the expansion, we immediately know the germ of these properties that that corresponds to it. So there is a unique germ on the whole domain that expands asymptotically in this scale. We cannot have exponentially small additions or other things. So this is what we'll call Dulac germs. Okay, I will just tell that there are let's say three types of Dulac germs. What does it mean? This is motivated by the classical typography of diffeomorphisms. So of diffeomorphisms around 0. We will call a Dulac germ. I didn't say it, but I should have. All the coefficients are real. That's because it here for us. That's because it comes from the real problem, from the real vector field. So all coefficients are real. So we can consider three types. First is A, Z plus. I'm back to the original variable. That means if this A is by modulus different than 1, we will call this hyperbolic. If this is different than 1, we call it strongly hyperbolic. And the other thing is what we call tangent to the identity or parabolic. Since coefficients are real, I covered all the cases except minus, but then becomes sort of jumping from one side to the other. We don't want it. So this will be called parabolic. Dynamically, this is the most interesting because if you just let me suppose for the moment that we consider just the first term that somehow captures well the behavior, dynamical behavior of this germ. And for example, let's say that we have a germ like this, say in the complex plane. What is the dynamics of it? If, for example, here is one half. If here is, for example, 2, we consider the inverse. What happens? We take one z. Z is now a complex number. We can put r e pi. When we multiply this, we see that we just make r smaller, and it stays the same. So in the linear case, this will be a trajectory. If we iterate, if we had it as a first return map, this would be the trajectory that accumulates. We have additional terms after, so this will it will slightly change. It will not go in a line. If we have Z alpha, we will have rotation that goes even more quickly to the origin. So these are sort of strong contractions that do not provoke more than trivial number of living cycles because of their strong contractivity. So dynamically for us, the most interesting case is this one. And what we consider is the following. The first thing is that we would like to classify such germs. Classifications are usually done first formally, and then we either try to prove the convergence of this, not convergence, but asymptotic, for example, Gevrey asymptotic properties of this series on some sector to be able to tell that there is a germ that expands asymptotically in this series. Or by some other means, we try to get the sectorially, or if we can, globally analytic classification, analytic linearization or normalization, and then somehow compare it to the formal normalization in a way to see how formal linearization is asymptotic expansion in some sense of the analytic linearization or normalization, depends on the germ. So let me just tell something that I forgot, and this is a notion of germs that I suppose you all know. What we germify are germs and domains. So standard quadratic domain is germified in the sense that any domain of this behavior will be the same. So we can just shift it as much as we want to the left, change a little bit these coefficients here, but the asymptotic behavior remains quadratic. And also we germify Dulac germs at infinity, saying that the two are the same if they coincide on sufficiently, or on no matter how small or big finite quadratic. So they are germified. Okay. And so let me recall you, they are not analytic at zero, they have logarithmic expansions, so they are defined on the open neighborhood of zero. And we don't have, like here, analyticity property of these germs at zero. So they are somehow defined on different domains, not on complex disks. Okay, so now the idea is to try to find normal forms of such germs. What is standardly done? Is finding the normal forms of homomorphisms at the origin. So in the, I will not talk about this hyperbolic case, they are linearizable or normalizable to the first term. But what is interesting to us is parabolic case. So in the case of germs that are analytic at zero, they have a Taylor expansion, etc. And the standard theory tells us that we can formally normalize to a germ that we can make this equal to zero by homotopy, and then let's say this is k plus 1, it doesn't have to be 2. Okay, so what I mean by formal normalization? By formal normalization, I mean that we apply a succession of changes of variables. First, homotopy, so it has to be a diffeomorphism, so it has to have the first term AZ. Then another one will be okay, so we increase, these are elementary changes, and we increase L every time so that we kill more and more terms. And at some point, by applying some big L, we don't change anything in the beginning. So at each point, we do one of changing variables like this, and we eliminate as much terms as we can. It is a classical procedure for vector fields, also for diffeomorphisms, that is based on Lie brackets, and I will not go into details how we do it, but somehow it's just a formal computation to see that everything can be eliminated except this. So we find this as a normal form. It depends on two things, k and rho. This is a multiplicity, and this is what we call a residual invariant. And also, there is another way of presenting the normal form as not formally the shortest form, but we want it to be a type 1 map of a vector field. So this is an analytic germ, but nobody guarantees that we can embed it analytically on the whole disk to a vector field that is also analytic in this disk. And this is actually in generic case not the case. So for a parabolic germ, it is very rare that we can embed it analytically in a vector field on the whole disk. What happens is that we can do it sectorially. Okay, we can find the field such that there are such that f embeds embeds differently on two in different fields on two petals or two sectors, and they have some exponentially small differences at their intersection. So this is a standard phenomenon. But okay, I would like formally to write a normal form that will formally correspond to this. And what we choose as a normal form is the following. I think it's rho minus k plus 1 over 2 zk. So, and this is some f0 field of z. So this means that it is type 1 map of this vector field d over dz. So once that we solve the equation z prime is equal to this and find this type 1 map, we get a germ like this. On the other hand, we can do it formally by expanding formally the formal exponential. So this is an operator. So we have first identity applied to identity, then this operator applied to z, then this operator applied to this operator to z. So we can expand it formally as formal exponential, and we will see that the first terms will be like this, and the others can be eliminated. So in this sense, they are formally equivalent, and we can take this as a formal normal form. So basically, we pose the same question here for the Dulac germs. So there are no more analytic. They are no more analytic, and we would like to deduce a similar normal form and similar embedding result as is done for standard analytic germs. There is two questions that we pose. First is normalization, formal normalization. Sure, what we have to choose here is with what changes of variables we work. We are ready. It's legitimate to choose just such changes, but then we will be left with normal forms that are much more complicated. Then we decide to also ramify by adding logarithms the changes of variables to be able to come to more or less the same form. So we can feel more by introducing logarithms in the changes of variables. So to finish this procedure, we need in the end to compose all these changes of variables. So what does it mean? It's formal composition, but it converges in a strong formal norm. strong formal metric. What happens is that once that you compose AZ with this and then add higher terms, we see that the initial part completely stabilizes. So what I want to say, L, for example, 0 to M, P, L, order of this becomes more and more big integer as M goes to infinity. So we have sort of strong formal convergence. It's formal, but it's a series that does not necessarily converge analytically at the disk, and this will not be the case usually. Sometimes it is. When it is the case, this means that the germ can be embedded in a vector field analytically on the disk. When this is not the case, we will have only sectorial analytic functions that expand in a divergent series on two sectors. So, but what we see here is that we have strong convergence, that this is actually not a trans series, it's a series because of just composing z plus z squared, z plus z3, z plus z4. It converges formally, strongly, and without notions, without introducing a trans series. So here we can add logarithmic changes. What we get is better normal form, but what we lose is this series property, because at this point we end up with a trans-serial change of variables. What becomes not a nice thing to have if we want to say what does it mean that analytic change on some sector expands in such trans-series, because then we have to give a summation rule at limit ordinal steps to be able to define the asymptotic expansion. So this is a problem that we encounter in Dulac germs. So first is formal normalization, and second is analytic normalization. That is the same as analytic embedded in a field. Will be sectorial, and somehow the relation. So can we somehow say that we have, once we have formal normalization, how to sum it to get the analytic normalization, or even less difficult question, once that we have analytic normalization, what does it mean that formal normalization is asymptotic trans-serial expansion? And what is the summation rule that we have to apply to give meaning to this notion, to have asymptotic expansion in a trans-serial scalar? Okay, so I will now just say a few words about this formal normalization. That we have a Dulac germ. I'll illustrate from one example, but not completely. So let's say that we have a very simple germ that is of Dulac type. I'll say what this. So L is a variable -1 over log z. What we want is that it is infinitesimal, so that the terms that come further are lexicographically bigger. We want to somehow have the lexicographic order. The lexicographic order is well adapted to the rate of growth of monomials. So that's why we exchange this to be infinitesimal. So what we see is we want now to eliminate the terms. The first term, like here, will never be possible to eliminate. And we apply changes of variables of a similar form, but we allow logarithms. Let's say either homotopy, either elementary changes that are of the type L, M, where L is an integer positive integer, and m is possibly negative integer. So this is a log germ since this is log z, so it's polynomial z. Everything is okay, but applying changes like this, we see that to eliminate term z3, we need a change. This cannot be eliminated as a first term. We need a change z plus z squared, I think L. Okay, once that we eliminate this, we have a problem. That once that we compose, what happens is that we generate additional terms, and this additional term will have z3L. So it will be the next one that is not bigger by power of z, but bigger by power of L. And what happens is, after this first change, we arrive at that. And additional terms that I now do not control, but they can be somehow controlled. Next change will eliminate this thing, will generate z3 L squared, etc. So what happens is that even to eliminate one term, we already need infinite depth in logarithms. So we end up with the formal change of the form. Let's say z az commodity plus z k, and then we have r l, where r is Laurent series. Even more problematic is that it does not converge at all. So it will most often have factorial coefficients. So this is trans-serial changes of variables, but luckily what happens is that it converges formally, and depending on the type of a germ that we have, we can have either strong convergence of a composition. That means more or less like this, that order in the z variable of this becomes bigger and bigger, or in something that we call a weaker topology, weak formal topology. That means, okay, it's not true that, the idea is that let's say we have a composition that is indexed by alpha ordinal. So strong convergence will say that for every power of z, we arrive at some ordinal, such that this minus ordinals up to this ordinal, let's say omega up to alpha k, will have order in variable z bigger than k, and this can be done for each k. This is strong, but we can have a weaker thing, and that means that if we look at this composition, as we add compositions, as we add further and further terms of composition, finally we can find one common well-ordered support. And what happens is that every coefficient of every monomial stabilizes at some point. So if we pick any monomial and we look at its coefficient, it will stabilize at some point in the composition, not changing anymore after some not finite, but after some ordinal part of the composition. Okay, so this makes formal sense, but analytically we don't see much at this point from this function. So the approach is the following usually. Somehow we are always led by dynamics. So in the case of diffeomorphisms, like here, if we want to make a normalization or embedding in a vector field, usually the domain where we can embed corresponds in a way to the dynamics that this germ displays. So this would mean germs like this on a circle around 0, they have everything is attracting. So we have, let's say, one attracting sector that is everything. Also, these hyperbolic germs display dynamics like this. They somehow at any point they have they're attractive. But this germ, let's say Z plus ZK, Z9, most easy Z2 plus etc. What happens? I will put minus here. What happens is when we do this, if we take orbit here, we see that it approaches 0, tap, 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 so this is attracting. If we take it here, it will be repelling. So actually, in the complex plane, what is formed are two petals. Petals are unions of sectors, looking like petals of flowers, which mean that sectors are decreasing radius as they increase opening. So unions of such sectors, but we can also consider sectors. So here is one attracting sector. For every orbit here, it will attract. For every orbit here, it will repel, meaning that F minus 1 attracts. So on the intersection of those, we have attraction here, and in negative time, attraction here. That means repulsion, attraction in real time. So sort of closed orbits in these intersections. So we see what we will have as a result also is that not linearization, but sending to a normal form will be possible analytically on each of these sectors, and both will expand asymptotically in a formal series that we have obtained. So we want to deduce the similar result here. And how we approach the problem is not that I would like sometime in the future to do it, but at the moment we did not do it. We didn't start from the trans series and try some resummation process, I don't know what, to, like in the standard case, it can be done by Laplace Borel, to a divergent series to get the sectors of convergence. So with this, we did not do that, but what we did is, using dynamics, we try to deduce the sectors of repulsion and attraction, try to construct in a different way analytic linearization, analytic normalization, or analytic embedding in a field. Everything is the same on these petals, and then see how this corresponds to the formal normalization. So sort of different approach. And what is easy to do is that once that we have a germ, parabolic germ of the Dulac type, this starts with Z alpha, then we can have some log Z or something like that. We see that somehow dynamically most important is this alpha that is bigger than 1. So it will behave exactly in the same way. So as here, if we have Z minus ZK plus 1, this will provoke petals of opening. Here is 2. We will have petals of opening 2 pi over 1. For K plus 1, we will have smaller petals, a lot of them, smaller ones intersecting, attracting, repelling of this opening. So here, similarly, we will have petals of opening alpha minus 1, but since this is defined on a Riemann surface of the logarithm, they will not come back and clash together, but they will somehow circle. So there are attracting and repelling petals. If I write it in this domain like this, we'll see this first is attracting. If I put minus here, for example, the first one is attracting, so we'll have the next one. So there are some orbits that will be closed as here, because this intersects with the repelling petal. And again, This is repelling and this is attracting. And there are some orbits that will just not go in that are not closed, that correspond to orbits like here, that are not closed, but it is the same, just like, say, they do not, there are some orbits that come like this also. Let's finish here. Okay, but it's the same dynamics, just written in the logarithmic chart at infinity. You can represent it also on the spiraling disks as intersections of petals where we have behavior like this, but there are infinitely many. Okay, so these dynamics suggest that we can probably normalize analytically on those petals, and how it is easier somehow to do it is by, instead of considering changes of variables, to consider something that is called the Petals coordinate. It comes back to solving a homological equation. So instead of changing variables, we consider the Petals coordinate. The idea is the following. What's the Petals coordinate? We take either a formal germ or a germ and search for either a germ or a formal thing that satisfies this equation. What does it mean? It means that it sends orbit z, f of z, f square z, etc. to translation. So in the variable, each orbit will correspond to a translation by one. So what we see, translation by one can easily, in this coordinate, be embedded in a vector field analytically, and this is the trivial vector field, d over dv. And then we can pull back to get the vector field in the original variable, but the problem is that this will not be global. And actually, how unglobal this is will determine how unglobally this can embed in a field in the original variable. So actually, the problem of embedding lies in this function. It is also very closely related. I will not now, it can be easily seen from the equation, but it is very closely related by, this is something that we explicitly know, to the change of variables. So by some change that we explicitly know that is based only on k and rho, or here alpha k, and so on some parameters that we know from the original germ, these two are actually correspondent. But the reason behind is that embedding in a field is actually going to translation variable, embedding in a field globally, and then returning by this to see where is the problem. So this should be sort of sequential. And so we can do two things. One is formal solution, and the other is analytic solution. Formal solution is easy to see somehow. F of z as a Dulac germ can be written, we call it clockwise notation. This means that we group all polynomials, all powers of logarithm together. So we work with this polynomial in L minus 1, etc. And we somehow do the clockwise construction of psi. First, so this can be expanded in a Taylor series. So this can be written as in the first approximation. Then there are some other terms after. So this is ZL squared minus etc. minus c of n equal to 1. So somehow the first power plus the logarithm of psi is deduced by the smallest part. And we see that psi prime of z is actually in behavior like z minus l 1 over L minus 1. And then we put here R to Z, and we go back and we continue. And imagine that you put the simplest case where this is equal to 1, and this polynomial is just one power, L minus 1. You end up with the equation 1 over Z and L is 1, like this. And if you try to solve it formally by partial integration, it is easy to see that we get out Z minus 2 from partial integration, but actually here we will have n factorial Ln. So this is a divergence that I was telling you about. So by formal integration, partial integration of this, it is easy to get this sort of series. On the other hand, I will finish shortly. On the other hand, we do analytic solution by passing to a variable that corresponds to the first term of the reduced P2 coordinate. So in this case, this will be Z minus 2. So only in powers, for example, it's some sort of approximation. So we can apply V as Z minus alpha plus 1 in the general case. So what we will see that in this variable, our P2 coordinate are F in this variable. So it's not the P2 coordinate, but very close to it. So F will behave very close to translation in this variable. And this is explicit. We don't need any kind of serious nothing. So it behaves almost like this. And then we somehow bound the remainder and prove that the invariant domain in this V variable will be sorted petal. And then when we go back by a change V or this will go back to our petals like here. And now this solution on one side this not formal gives us the algorithm which will attribute to this first limit ordinal in summation method that is based on analytic solution of the same equation, part by part. This is a sufficiently good summation method and the one that we need to be able to say that psi extends in psi hat. So this is
Thank you, Maja. Are there any questions?
So you said that in the classical analytic case, so the dynamic is understood via Borel-Laplace summation, right?
So the dynamic can be understood in the same way as here.
Yes,
so
that was my question.
there is a way to do it like this.
Yeah.
Or the other thing is that in this classical case, the P2 coordinate exhibits the Zagreb type. So you can resum it by Zagreb Laplace and get
It is even not only Zagreb, but it is even summable.
And what we somehow only on basis of the series that is formal, one can deduce the sectors by using this Borel Laplace. While here, I would very much like to do it, but somehow. So what we do is the geometric approach and then compare it, but I'm not able from the formal series, trans-series schema that they have here by some sort of adaptation of this.
Summation.
Get the summation on sectors that I want on this 2 pi or alpha minus 1 sectors.
Are there any other questions? Okay, so that's Maja. And there will be a question session on coming up.